Okay, so adding and subtracting complex numbers then. Let's look at that first. That's dead easy. 3 plus 2j plus 4 minus j, for example, equals. You just add the real parts and the imaginary parts separately. So that's it. 3 plus 4 is 7. 2j plus minus j. Minus j means one lot of j. So 2j plus minus j is 1j. Or plus j. We don't bother to put the 1 in. Like algebra, we wouldn't put the 1x in. So that would be the answer. Okay? Six plus 5j minus 3 minus 2j equals. The only thing we have to be aware of is the signs, particularly the double negative. So what will this be? Three, no. Before into the double negative trap. 5j minus 2j is plus 2j, so 7j. So apart from the fact that sometimes there's the double negative we've got to be aware of, and that will come, of course, when we're subtracting, then that's dead easy. Okay. Three angle 48 plus 5 angle 25. Say we're in polar form, like this. Okay. Yeah, angle. Remember we talked about these names. With 3 in this particular one is called the modulus. Anybody remember what this one's called? Argument, right. Okay, so 3 argument 48, we could say. But often we say this would represent a phase angle in electronics, so angle or phase angle. Yeah. This one, not possible. You can't add or subtract in polar form. So what do you do? Convert. Okay, yeah. So to do this, we have to convert 3 angle 48 to rectangular form and 5 angle 25 to rectangular form, and then we can add them. So would you like to do that? Right, so this first one, because we've got 48 degrees, we're going to be in quadrant number 1, thinking of this. Quadrant 1, 2, 3, 4. So I'd expect the real and the complex bits both to be, or so real and imaginary bits to be positive. So we'll get the answer. So what do I get for this one? So we convert each one to rectangular form, which is this plus this. Add them together and we get this. Of course, if we're working in polar, these were our original values in polar form. It's likely, and particularly electronics, that you want your answer in polar form. So the final job is to convert back. So if you could just do that. So that gives us a modulus of 7.8 and an argument or angle of 34 degrees to 2 significant figures. Okay. In polar form, multiplication is dead easy. All you do is and I'll write this down as a statement. Let's use blue. You multiply, so I use this abbreviation for multiply, MLT, that's common. Multiply the moduli. That's got a nice ring to it. You multiply the moduli, the numbers in front. So 3 times 6 is 18. And add the arguments. Angles. 48 plus minus 84. So what's 48 minus 84? And that will be the angle. straightforward, isn't it? Multiply the moduli and add the arguments. So you get 6 3s are 18. Angle 48 minus 84. 48 minus 80 is minus, oh, I can't do it, minus 48. That's not right, is it? Is minus 36. We can also multiply in rectangular form, and we're going to have a look at an example of that. As far as the assignment's concerned, you need to demonstrate you can do it both ways, which is why I'm doing it. Okay? But there is an argument for saying this is so easy, this, in polar form, why not convert our numbers in rectangular form to polar, because we can do that quickly on the calculator, do the multiplication in rectangular form, polar form rather, and convert back, and that's perfectly acceptable. In fact, when you get onto electronics, that's probably what you'll do. But you can multiply in rectangular form, so let's have a look at how that works. So in rectangular form, let's try multiplying these two numbers in rectangular form. So let's convert these two numbers that we just do, the examples we just looked at, into rectangular form, and then we'll do the multiplication and see if we get the same answer. So can you just convert these two to rectangular for me? Okay, so to multiply them, you treat it like brackets in algebra. So we just multiply out the brackets, and we get 2 times 0.62 is 1.24. 2 times 5.9, so 2 times 0.62 gives us this bit, then you do 2 times minus 5.9, 2.2j times 0.62, and then that times that. So you multiply everyone in the first bracket by everyone in the second bracket. So 2 times minus 5.9 is minus 11.8j. 2.2 times 0.62 is, so that's plus 1.36j, and then 2.2j times minus 5.9 is minus 12.98. Thank you. J squared, yes. Okay? Because j times j squared. Okay? Now, remember this. This is the key to this. What's j? Right, the imaginary number, which is square root of minus 1. So question, if j is the square root of minus 1, what's j squared? Minus 1. Well done. Because that's the whole point, that's the definition of it, is it? This j is the square root of minus 1, so if I square that, I'm going to get minus 1. So that means that suddenly this last bit becomes a real number, because j squared is minus 1. And we get 1.24, and we can collect together these imaginary numbers now. Minus 11j plus 1.36j is minus 10.44j minus 12.98j squared becomes plus 12.98, because j squared is minus 1. You see that step? In fact, that's always the consequence. When you end up with j squared, what the effect of that is, you just change this sign from a minus to a plus, or if it's plus, it goes to a minus. So it's always, that's always what happens. So this becomes suddenly plus 12.98, and the j squared's gone. Now I've got two real numbers that I can add together. So what's 12.98 plus 1.24? No, 14.2. Yeah. 14.22 minus 10.44j. And suddenly we've got a complex number with a real part and an imaginary part, and that's the solution. As a check, convert this back to polar, we get So we go shift polar, put those numbers in, and we should get within a bit the answer we got before, which is 18 angle negative 36. Yeah. Angle, sorry. So which is it positive or negative, Richard? You see, so how easy it is to miss that negative sign. So if you make sure you think about which quadrant you expect to be in, then you won't miss that, okay? So last rule we need to look at then is dividing. There's an example, divide in polar form, so we'll look at polar first, because as with multiplication, this is much by far the easiest way. So in practice, you might, well, if you've got to divide complex numbers, convert to polar if you're not in polar, and then we do the division that way, and then convert back. But you can convert in rectangular form, as we'll see. Now, if you remember the statement we wrote down for the multiplication, what do you think I'm going to write for the division? Right, so what do I do with the moduli? Nope. Divide the moduli and subtract the arguments, yes. Yeah. So we've got to be careful, because we might well, as we're subtracting the angles, we might end up again with a double negative, okay, which you have in this example. So be careful, beware the double negative again. Apart from that, it is straightforward. 15 divided by 5, I tried to make the example quite easy, is 3. But the angle, 48 minus 20 is plus 20, so 68. 48, remember we subtract the angle, so it's 48 minus 20 plus 20. Let's look at an example of dividing in rectangular form. We won't use the examples we had before because I want to keep the numbers straightforward, so let's just make one up. 3 plus 2j divided by 4 minus 3j. Bless you. So what we do is, we use a trick to do this, so that the number underneath disappears. The complex part, rather the imaginary part of the number underneath, disappears, and we're left with just a real number. And when we do that, we see that we can write the answer quite straightforwardly, as we'll see. So we use a trick to get rid of the imaginary part of the number at the bottom. And that trick is to multiply the bottom by what's called the complex conjugate. And all that means is it's the same numbers, 4 and 3j, the complex conjugate. But instead we just swap the sign. So as this is minus, it becomes plus. If it had been a plus here, it would have become a minus. So that's called the complex conjugate. And as we'll see, the consequence of this is, when we multiply out 4 times 3j, 12j, minus 3j times 4 gives minus 12j, and they cancel. So you're getting rid of the imaginary bit at the bottom. So we do this trick to get rid of the imaginary bit at the bottom. If we do that, though, we must also multiply the top by the same thing, because otherwise we'd be changing the division. We can do what we like in a fraction to the top, so long as we do the same to the bottom. So you multiply top and bottom by this thing called the complex conjugate. The name's not important, but there it is. In fact, the conjugate means the same numbers in the bracket but opposite sign. And just in this case, because they're complex numbers, it's called the complex conjugate. So what we do is we say, right, that means that we can now say on top we can multiply out these brackets. 3 times 4 is 12. 3 times 3j is 9j. 2j times 4 is 8j. 2j times 3j is 6j squared. Over 4 times 4 is 16. 4 times 3j is 12j. Minus 3 times 4 is minus 12j. And minus 3 times 3 is minus 9j squared. So we just multiply it like we did in the multiplication. Collect together imaginary numbers on the top here. And remember that j squared is minus 1, so that changes this sign from a plus to a minus 6 at the end. And we end up with 12. 9 plus 8 is 17. J minus 6 over 16 minus 9, the j's have gone, minus 9 times minus 1 is plus 9. 12j minus 12j, 0. And that's the whole point of doing it, so that those disappear. Okay? By multiplying by the complex conjugate, they disappear always. If they don't, you've made a mistake. Now here's the trick. If we look at this, trying to get this on the board as well as that. If we look at this number, sorry, it's plus 6 times j squared. J squared is minus 1, remember, so that makes that minus 6. Oh yeah, I've not finished, so we'll do that then, you're right, yeah. But looking at the trick, so the trick that's involved here, I said there was a shortcut. If you look at this number that's underneath, this 4 and the 3, it doesn't matter what those numbers are, this number is always the first number squared. So 4 squared is 16. And the 9 is the 3 squared. And it's always plus. So before I start, I know that the bottom number is going to be 4 squared plus 3 squared, and I can put that straight underneath. So that's the shortcut. And when you do it, it still works out. Because you're doing the complex conjugate, this will then become a minus. So you're still ending up with minus at the bottom, which when you times by j squared gives the plus. So it always turns out to be plus. So there's your trick, or your shortcut rather. So therefore this equals 12. As Ben is saying now, we can say, okay, 12 minus 6 is 6. Plus 17j over 25. And this 25 is easier to arrive at. You don't need to do all these steps. Because you're multiplying by the complex conjugate, this will always be the case. Always the first number squared plus the second number squared, so we get 25 underneath. Now, the reason why we try and get rid of the imaginary number underneath, now that we've only got one number at the bottom, we can actually split this fraction and call it 6 over 25 plus 17j over 25. And if we work out what they are, we've got the answer. So 6 divided by 25 is 0. Divided by 100, which is 0.06 times 4 is 0.24. And same for that, divided by 100 is 0.17, times that by 4, 68. And that's the answer. Okay? And that technique always works. Yeah, this will always work out to be positive. What, this here, do you mean? No, because I could have at the top here, this could be negative, so we could have a minus in here. And this, when we add them to numbers together, that could have been a minus number there, and so we could have a negative at the start. So yeah, you can have different signs, but the bottom will always be, yeah, that squared, and it will always be these two numbers squared and added together. Okay, so what we can do now then to check in this form is to convert this to polar. So convert this as a check for me and give you a bit of practice. Convert that to polar, convert that to polar. Do the polar division using the first method we had. Divide the moduli and subtract the angles, and then convert back to rectangular and see if you get this answer. You should do within a bit.